start the recording. Desktop audio is being recorded. Nice. Welcome, welcome. How's it going, Zach? All right. So let's go ahead and hop right into this. Let's start talking about Ampere's law. But first off, sort of a throwback to a month ago, Gauss's law. What was Gauss's law again? Can someone sort of give me a run through as to what Gauss's law is? Should probably open up Paint. Ooh. Boom, there we go. What is Gauss's law again? Remember, throwback to our last units with electric fields. And remember the closed surface integral of E dot dA? What does that end up equaling? Where Gauss's law is, we have our closed surface integral of the electric field dot product with dA of the surface, and that equals the enclosed charge over epsilon naught, right? And how can we use that to find electric fields for certain charge distributions? Right, if we have a symmetrical charge distribution where the dot product of E dot dA for all the points is going to be either 1, so E times dA with the cosine of theta being 1, or it's going to be perpendicular where the cosine of theta is 0, and we can find our electric field for symmetric charge distributions. Now, why would I be bringing Gauss's law back up here if we're talking about Ampere's law here for Unit 19? Gauss's law is for electric fields. How is it similar to Ampere's law for magnetic fields? Yep, Ampere's law is the integral of B dot product dl. And what does it end up equaling? It's mu naught times I enclosed. Yep. So it's sort of similar to Gauss's law. And how are the two laws sort of connected? Are we able to use Ampere's law similarly to how we would use Gauss's law? Where we use it to find magnetic fields? Is that how it works? Because they both use cosine of theta. What do you mean cosine of theta? How do they both use the cosine of theta? the dot product of both elements equals, for example, in Ampere's law, B dl cosine theta. Yep, exactly. Because the dot product simplifies to where if we want the magnitudes, it's the magnitude times the cosine of the angle between. And now, how can we simplify that cosine theta argument? For, like, what sort of situations are we able to actually use this B dot dl integral? What sort of situations are we able to use Ampere's law in to find magnetic fields? Symmetrical cases, exactly. That's the main thing I'm looking for here. Where we have symmetrical charge distributions, where we use Gauss's law, and for Ampere's law, we have symmetrical current distributions, and we can use both laws to greatly simplify how we find our generated fields. So let's go ahead and hop into a quick little review example from Gauss's law, where we're just going to have a uniform sphere of charge, radius A, total charge minus Q. So we're going to have our radius A, total charge minus Q, at the origin, surrounded by a conducting shell. Horrible drawing, but you get the picture. And total charge plus 2Q out here. So what would be the magnitude of the electric field for R is less than A, so inside our insulating sphere of charge, between the sphere and the conducting shell, within the conducting shell, and then also outside the conducting shell? Let's say 10 minutes, then we'll go over it. Just a quick little review from last month. So how would we actually go ahead and find our electric field at each of these four locations? Let's start, first off, let's start outside of the entire, we'll start outside of the conducting shell. So out here with R greater than C. How do we find the electric field there? Use the other version of the formula where E is equal to KQ enclosed over R squared. Exactly. And we get that formula, we can actually derive that from Gauss's law. But, you know, we've already done that in the past, but you're right. So we just use E is equal to K times Q enclosed over R squared. The total enclosed charge is just plus 1Q, right? So for D, E is equal to KQ plus KQ over R squared, because the enclosed charge is just plus 1Q, because we have minus Q in the center and plus 2Q on the outside. So in that case, what would be the electric field between the conductor and our insulating sphere? Yeah, you're right. For inside the conductor, it's going to be 0 because we're inside a conductor. There's 0 electric field. You're right. And what about between the conductor and the insulating sphere? It's going to be negative Q. Yep, exactly. And then what about inside the sphere itself when R is less than A? How do we find the total enclosed charge when we're inside our sphere? Q enclosed is equal to the density times the volume enclosed. Exactly. And so how do we get the density? We're just given the total charge. So how do we get the density? Is equal to total charge over total volume. Exactly. So we have our density is going to be negative Q over our total volume. What's the volume of a sphere? Four-thirds pi r cubed. Exactly. So we have our 4/3 pi, and the radius here in this case is a, pi a cubed. So then our electric field is going to be K times our Q enclosed, which you said was the density times the enclosed volume. What would the enclosed volume end up being here? It would just be the 4/3 pi r cubed, right? For whatever radius we're at. So we have our density times our volume. The 4/3 pi cancels out. So we have negative Q times r cubed over a cubed. K times Q enclosed over r squared. So that ends up being negative K Q R over a cubed, because our r squared cancels out. Right? Nice and easy. That's just some basic review from last month with Gauss's law, where we're finding the electric field based on enclosed charge. So now let's go ahead and actually hop into an example where we're going to go ahead and find the magnetic field using Ampere's law, and it's essentially the same exact thing. It's just instead of enclosed charge and electric fields, it's enclosed current and magnetic fields. So we're going to have a long solid wire of radius A carrying current I1 into the page. So let's go ahead and draw this over here. I'll use the actual shapes. So we have our wire of radius A. This is a cross section of it, carrying current into the page. It's going to be surrounded by another concentric wire with inner radius B and outer radius C, if I can, something like that. And we're going to have the outer wire carrying current I2 out of the page. So how would we go ahead and find our magnetic field at each point along our, at each point as we go out? Let's say just along the x-axis here, to keep it simple. So let's go ahead and take 10 minutes and we'll talk through this. Let's actually say that I2 is half of I1. So we have I2 is going to be I1 over 2. Just to keep things easier. The magnitude, obviously. They are running in opposite directions. Let's go ahead and take 10 minutes, and then we'll talk through this. I want to find the magnetic field at each point as we go out along the x-axis. All right, so we want to go ahead and find our magnetic field at all our different points along the x-axis. So first of all, let's just worry about finding the magnitudes of the magnetic field. Why do we just want to worry about the magnitudes initially? The direction's pretty easy to find afterwards, right? How do we find the direction? Right-hand rule, exactly. But let's worry about that after we found our magnitudes. So how do we go ahead and find... Let's start off, first of all, outside of the entire current distribution. So out here with R greater than C. So how do we go ahead and find our magnitude of our magnetic field out here? How do we use Ampere's law to find it? Mu naught I enclosed over 2 pi r. And how did you get that? How do we actually derive that from Ampere's law? So if we want to go ahead and actually derive mu naught I enclosed over 2 pi r from Ampere's law, what do we need to do? How can we simplify this integral? Bring b outside the integral because it's a constant. First, we need to get rid of this dot product, right? How do we get rid of the dot product? Because then, yeah, we can bring b outside the integral. B times dl times cosine theta. Exactly. And what does our cosine theta end up being? What's our angle theta? Theta is either 0 or 180 depending on the direction of our magnetic field. Exactly, because we're essentially drawing I'm just going to use the term Gaussian surface because it's essentially what we're doing. And we're going to draw it out here. And we're integrating our line integral along that entire Gaussian surface, essentially. And what we end up finding is that the magnetic field is always, parallel or anti-parallel to this line integral. So cosine of theta is, theta is either 0 or 180. So the cosine just becomes, plus or minus, depending on what direction it's in. Essentially, it ends up being 1. So we can simplify it. B dot dl is equal to b times dl. B comes out because it's a constant. And our integral of dl over this entire circular path, what does that integral give us? Exactly, it gives us the circumference of the circle, which is 2 pi r. Boom, exactly. We've gone ahead and simplified our integral down, and then we know that this is equal to mu naught I enclosed. So then B is equal to mu naught I enclosed over 2 pi r. Nice and easy. And now we can just go ahead and at any point find what the enclosed current is, and from that go ahead and find our magnetic field, at least the magnitude of it, and then we go ahead and we use the right hand rule to find the direction. At least that's what I recommend. Find the magnitude, then find the direction. So outside of the entire thing, when r is greater than c, call this IV, we know that B is going to be, we have mu naught I enclosed is our I1, and then I2 is traveling opposite of it. So we have I1 over 2. So we have mu naught I1 over 2 times 2 pi r, so 4 pi r. And what direction is our magnetic field going to be traveling in? Use our right hand rule here. What direction is this magnetic field going to be in? Be clockwise, exactly. Because we know I1 is greater than I2, so we stick our thumb in the direction of I1, which is into the page, rotate our fingers around, and we find it's clockwise. So in this case, we're gonna, because we're finding it along the x-axis, clockwise is going to be down in the negative y direction. Exactly. So now what about the magnetic field between the two wires? So not inside the second wire, but between the two wires, between A and B. It's just yep, it's mu naught I1 over not r squared, but 2 pi r. You're getting mixed up with Gauss's law. That's fine. I know what you're going for. But and then we know it's once again right hand rule. It's in the same direction as out here. So negative mu naught I1 over 2 pi r, negative y direction. Now what about inside the inner wire? We're gonna worry about between B and C for the last example because it's the most annoying one in my opinion. How do we find the total enclosed charge if we're at r is less than a? Use the current density to find I enclosed first. Exactly. And how do we get the current density? What's our current density, J? Exactly. That's our current density per area is our total current, which it's I1, over our total area, which is, what's the cross section of a circle here? What's the cross section of our cylinder? Our cylindrical wire? Yep, pi r squared. And in this case, our radius is a. Pi a squared. So then we get our magnetic field is equal to negative mu naught over 2 pi r times our enclosed current, and we get our enclosed current by multiplying our current density times the enclosed area, which is I1 over pi a squared, our current density, times the enclosed area, which is pi r squared for whatever radius we're at. That ends up becoming pi cancels out here. 1r cancels out. We get negative mu naught I1 r over 2 pi a squared y hat direction. All right, nice and easy. It's basically Gauss's law all over again for currents. And so then how do we go ahead and find the enclosed current if we're between B and C? So we're inside this section here. How do we find our total enclosed current?
In that case, we gotta break it up even more, especially looking at the enclosed current by looking at the one like at the very center of the origin, and then the fractional portion that is within our circle for the second current.
Exactly. So let's first of all start. How would you first approach this? Let's start with, let's just add on the enclosed current inside the center at the end. So first of all, how do we find that fractional enclosed current for the outer part?
We have to calculate J for the outer one.
Mm-hmm. And so how would we do that? Let's call it J2.
We would take the original current of the total and then divide it by the area of that that one. So that would be pi. I think the outer one is B, so pi c squared minus pi b squared.
Exactly. Pi c squared minus b squared. And then we have our total current, which is I2. And then we know that that's going to be running in the opposite direction of our I1. And we know it's I2 is going to be half of I1. So then what we end up getting to get our enclosed current is going to be I1 minus, because we know our enclosed current from the outer part is going to be in the opposite direction, minus I1 over 2 pi, because I substituted in I2 is equal to I1 over 2, c squared minus b squared, times our total area outside, which is pi times what? Our total enclosed area, if we're at an arbitrary distance r that's between C and B.
R squared minus, what's the other one again? It's B, right? So
yep.
Minus B squared?
Yep, r squared minus b squared. Exactly. So we get our pi cancels out, and we have this ugly ratio of r squared minus b squared over c squared minus b squared that unfortunately isn't really easily simplified, but that's fine because it's all things that we could technically measure. So then B would be negative, because we know it's going to be in the negative y hat direction, mu naught over 2 pi r times our enclosed current, which we know is I1 times, and we'll plug this all in, 1 minus r squared minus b squared over 2 c squared minus b squared. Right. I've just pulled out the I1 and put it here, so then we have the 1 minus. Pi's cancel out. It's r squared minus b squared over 2 c squared minus b squared. Does anyone have any questions about this? All right. So in that case, let's go ahead and throw in a few numbers here. And so we're going to have A is equal to 1 centimeter, B is going to be 2 centimeters, C is 2.5 centimeters, I1 is going to be 700 milliamps, and I2 is going to be 400 milliamps. So how do we actually go ahead and find our magnitude and our x and y components of the magnetic field at -2, 1? So it's like go out 2 and then up 1. So somewhere right about there. Let's go ahead and let's take about, let's say 5 minutes, and then we'll go over this. So first of all, we want to find the magnitude, and then we also want the x and y components of our magnetic field. Take 5 minutes, then we'll talk about it. All right, so how do we actually go ahead and find, first of all, how do we get our magnitude of our magnetic field at -2, 1? Would just be the exact same process as for R is between B and C, right? And we just plug in our numbers, where instead of I2 being I1 over 2, it's slightly more than half. But we can essentially just take our work from here and plug it in, right? Just substitute in the numbers. So we'll go ahead and do that. It's going to be a bit annoying. We have mu naught over 2 pi r, where our radius is the square root of 5, right? Because the square root of 1 squared plus 2 squared. What's mu naught again? What's the value of mu naught? It's like 4 pi times 10 to the -7, right? So 4 pi times 10 to the -7 over 2 pi is 2 times 10 to the -7 divided by our radius r, which is the square root of 5 centimeters. And square root of 5 centimeters, if we want to convert that to meters, we have a 10 to the -2 on the bottom, so we'll take that 10 to the 2 on the top here. That's the mu naught over 2 pi r, and then we have I1 minus I2 times r squared minus b squared over c squared minus b squared. So we have I1, which was 700 milliamps, so 0.7 amps, minus I2, which is 400 milliamps, times r squared minus b squared, which is 5, square root of 5, so it'd be 5 times 10 to the -4 times 10 to the -2. How do we actually convert this centimeter squared to meter squared? Does it end up mattering because we have the ratios on the top and the bottom? It does not. So we have the r squared, square root of 5. So 5 minus b squared, which was, b was 2. So 5 minus 4 over c squared minus b squared. C was 2.5. So 2.5 squared minus b squared, which is 2 squared, which is 4. And that ratio. And so we get a total magnitude of about 4.7. Let's move this over here. We have B. We have about 4.7 times 10 to the negative 6. So 4.7 microteslas. Right. Anyone have any questions about that? It's basically just plug and chug into a calculator. So then how do we actually go ahead and break that into x and y components? What direction was our magnetic field in again? Is it clockwise or counterclockwise? Right-hand rule, I1 is into the page, I2 is out. I1 is the dominating current. So then we point our thumb into the page, rotate our fingers, find it's clockwise, and this is the origin here. We go out 2, go out 1. This is where our point is, and we know the magnetic field is always going to be perpendicular, so it's going to be up in that direction, right? We have 2, 1 here. So how do we go ahead and actually find the x and y components here? Well, first off, I'd say let's start with finding this angle here, theta. Theta is equal to what? SOHCAHTOA, tangent of theta is opposite over adjacent. So tangent of theta is 1/2. So we have the inverse tangent of 1/2. That comes out to be what? It comes out to be about 26.5 degrees. So we'll call it 27 degrees. And now, is that this same angle here? Or is it this angle here? Which angle is this same theta? Gonna be 1 or 2?
Isn't it 2?
Yep, exactly. We just, apply trigonometry. We have this angle is theta, which means this angle is 1 minus theta, which means this angle is theta, which means 1 is 1 minus theta, which means 2 is theta, once again. So then our x component would be our magnitude b times what? The sine or the cosine of theta?
Wait, don't you mean 90 minus theta?
You're right, 90 minus theta. But you know what I mean. Yeah. We have,
I do, yes, I do.
Yeah. But so essentially we just go around and we find which one's theta. But so for the x component, is that going to be b times the cosine of the angle? or the sine of the angle? SOHCAHTOA, sine is opposite over adjacent. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Opposite here for this angle. Opposite would be x, and adjacent would be y. So x is going to be b times the sine of theta, and y is b times the cosine of theta, which we go ahead and plug in. We have our magnitude here. We'll just have the 4.67 microteslas times the sine of theta. Sine of theta is 1 over root 5, right? Because our hypotenuse is square root of 5. So our x component is going to be about 2.1 microteslas, positive x. And our y component is not 1, but 2 over the square root of 5, because adjacent over hypotenuse. Y component is about 4.2 microtesla. Once again, positive. You guys have any questions about this? Essentially what we've done is we found our magnitude using Ampere's law, right-hand rule to find the direction, and then trigonometry to find the angle, and therefore break it down into x and y components. Hey, if you guys don't have any questions, that'll probably be it for the session today. I do have one more example, but I'll probably end up pushing that over to tomorrow, and we'll go over it tomorrow. And it's going to be using Ampere's law, and once again, where we had multiple examples of symmetry with Gauss's law, we also have multiple examples with Ampere's law. But that's it. Then, if you guys don't have any questions, then that's going to be it for the session. Hope this helped you guys out a bit. Same time tomorrow, actually on time tomorrow, 1 o'clock, hopefully, maybe. Can't guarantee 100%. But thanks guys for coming. Hope this helped out. See you guys around.
Thanks, Dylan. It did help.
Thanks. Always feels good to know it's helping out.